Have you ever wondered how a circuit remembers its past, especially when analyzing sudden changes or transient behaviors? It is a fascinating aspect of electrical engineering where the history of a component directly impacts its future response. When using the Laplace transform for an inductor, incorporating its initial current is achieved by including an additional term in its S-domain representation. Specifically, the voltage across an inductor is given by L multiplied by the derivative of its current with respect to time in the time domain. In the Laplace domain, this transforms into V of s equals Ls I of s minus L times I of 0, where I of 0 represents the initial current flowing through the inductor at time t equals 0. The reason for this additional term directly reflects the inductor's fundamental property. It stores energy in its magnetic field and resists instantaneous changes in current. This stored energy at the initial moment, represented by the initial current, must be accounted for to accurately model the circuit's behavior. The L times I of 0 term acts as an equivalent voltage source in series with the transformed impedance of the inductor, ensuring that the circuit's energy state at the beginning of our analysis is properly carried forward into the S-domain. To practically incorporate this, first determine the initial current I of 0 through the inductor just before the event that changes the circuit, such as a switch closing or opening. Then, when drawing your S-domain equivalent circuit, replace each inductor with an impedance of Ls in series with a voltage source. This voltage source has a magnitude of L times I of 0. The polarity of this voltage source depends on the direction chosen for the inductor current. If I of 0 is positive in the assumed direction, the voltage source should be oriented to oppose that current flow, like a battery discharging through the inductor. This elegant method transforms the initial stored energy of the inductor into a convenient equivalent circuit component. It allows us to solve complex integro-differential equations using algebraic manipulations in the S-domain. Without this critical L times I of 0 term, our Laplace solutions would only describe the response from a completely de-energized or relaxed state. Understanding this ensures your analyses accurately reflected real-world circuit dynamics, especially during power-up or switching events. Ultimately, by correctly including the initial current term in the inductor's Laplace transform model, you gain the power to precisely predict a circuit's transient and steady-state responses. This ensures that the continuity of energy storage within the inductor is always preserved in your mathematical solutions, leading to robust and accurate circuit analysis.